and welcome to this workshop, Sonifying Space, Sonification and Immersive Audio in Max MSP. Have you ever wondered what data sounds like? Maybe, maybe not. In this hands-on workshop, you'll learn to use NASA data to turn solar storm activity into immersive sound. We'll dive into Max MSP to map solar storm data to sonic values like pitch and texture, and then we will use the IRCAM Space toolkit to map it into spatial audio. Along the way, you'll learn the basics of sonification, data parsing, and 3D sound design. Come build your own sonic universe and experience the sun like never before. My name is Monica Bolles. I am an audio engineer and sound designer, a digital artist and composer with a special focus on immersive experience and design. Feel free to check out my website to see some of the work and events that I have coming up. I've been working with spatial audio since 2011, when I first gained access to my local planetarium's 15.1 surround system. In 2016, I was accepted to the spatial music workshop at Virginia Tech's Cube, where I got the chance to compose for their 140-channel audio system. Since then, I've developed many custom toolsets in Max MSP to engage emerging technologies and craft textured soundscapes that explore space, movement, and interaction. As both a technician and artist, I've collaborated with artists and composers to bring their work into immersive spatial environments, while also producing my own large-scale multi-channel installations and live productions. I co-host the Immersive Audio podcast, as well as the spatial audio meetups through NOTAM, the Norwegian Center for Technology, Art, and Music. I also frequently curate, moderate, and present workshops and panels on spatial audio, full dome, and other immersive design topics. I'm going to talk a little bit about my work now. Resonant was my final thesis presentation for the Atlas Master's program at CU Boulder. It was a 360-degree immersive audio-visual performance that explored the concept of resonance through multiple lenses: physics, psychology, art, and music. I designed the experience to fully envelop the audience inside a circular scrim projection mapped in 360 degrees, paired with an 8-channel spatial audio array. Live music and contemporary dance performance were woven into the environment, creating a layered multisensory narrative. Through this work, I asked, what does it mean to examine a single subject like resonance from multiple perspectives? And how can immersive performance help us experience those differing perspectives in a tangible way? In 2019, I worked on a collaborative multimedia live performance piece called Intopia. It was designed for full dome and other immersive environments, and it featured groundbreaking work of musical artist Janet Feder. She's world-renowned for her pioneering compositions for prepared guitar. In this project, I focused on the spatial audio design, developing custom effects that allowed us to manipulate Feder's sound in real time using an iPad and Menu gloves. This setup dissolved the traditional boundaries between performer and audio engineer, allowing artist and technician to engage as true collaborators in the sonic space. Visually, our team experimented with photogrammetry and LiDAR scanning techniques to create interactive content that responded in real time to both the live music and spatial audio gestures. The result was a fully immersive audio-visual experience where sound and image were tightly interwoven, reactive, alive, and responsive to the performance. In 2020, I worked on a piece called Collision. It was a commission by the Playground Ensemble and is for cello, violin, electronics, and visuals. It has been showcased as a feature composition in the SPACE program, which is a 360-degree multimedia concert experience designed for domes. Collision is the sonic telling of a story about two lovers with the gravitational force of a black hole, slowly orbiting each other over time, getting closer and closer until one day they collide. For this piece, I sonified data sourced from current black hole research and juxtapositioned the cosmic phenomenon with a metaphor of human connection and intimacy. And my latest project that I worked on is Elegy's Enigma. It is a multimedia performance that blends immersive audio, live aerial cello with visual storytelling to explore themes of identity, memory, and the ethical entanglements of emerging technologies. The project was developed in collaboration with Cellista during our Atlas B2 residency at the end of 2024. The project merges science fiction and fantasy with personal narrative, weaving together sound, movement, and interactive media to question what it means to be in an evolving digital world. So for this workshop, you're going to need a computer, headphones, Max MSP 8 or up, and Max packages, IRCAM Spat tools, and Cinmat OSC package, and then optional multi-channel audio setup and Touch OSC or another OSC device. To be able to download Max, you can go to cycling74.com. Currently, we are on Max 9, and if you've never used it before, don't feel completely intimidated about this workshop. I would encourage you to do a few tutorials about just using Max and kind of the basics around it. But you can definitely kind of try to dive in with this. So download it from the website. They do have free trials, so feel free to look into it and just see if you like it. The next thing that you will need to download is the Spat IRCAM tools. So you will go to the IRCAM website and look for the Spat tools. The link will be included. And you will just need to create an account. They won't let you download without creating an account. And then once you've created it, you can download Spat 5. And that will be kind of the newest one is the best. They have Mac OS and Windows 64 downloads available. Now, once you've downloaded the Spat files, you're going to need to come into your documents or kind of wherever your Max 9 folder is. And you go into your Max 9 folder, and then you can go into your packages and you can drop the Spat 5 folder just directly in here. And this is how Max will know to recognize that your folder, that Spat 5 is installed. So with the OSC Cinmat objects, all you need to do for that is actually show your package manager. And so you can actually just download these directly from the package manager. And so you can look up ICST, you can look up Cinmat, wrong tool set. And this is the one that you're going to download. So you can just click on this and then there'll be an install button here, install it, and you will then have all of the packages that you need to be able to work with this workshop. All right, the first topic that we're going to cover today is called Sonification. So what is Sonification? Most people have heard of data visualization, but data sonification maps data to different sonic values to convey and perceptualize information and data. It can be used as an alternative or complement to data visualization. Sound can reveal patterns, trends, or anomalies that might be missed visually and can engage our auditory perception, which is temporal, immersive, and spatially rich. And so why would we sonify? Humans are excellent at detecting subtle changes in sound, such as pitch, rhythm, and timbre. It is useful in situations where visual attention is limited or not possible. One of my favorite reasons to sonify is that it creates new ways of engaging with scientific, environmental, and abstract data sets and can potentially help us gain different insights than we might otherwise. It also can enable emotionally resonant experiences with data through creative design. So applications of sonification. You can use it for scientific research, art and music, accessibility, education, as well as monitoring systems like alerts and system status in aviation, medicine, or finance, as well as within cars, and that's probably where most of us have experienced it. And so the sonification techniques that we need to think about are parameter mapping, assigning data values to sound properties like pitch, volume, spatial location, timbral properties, model-based sonification, using physical or mathematical models to generate sound from data, auditory icons and ear cons representing events or categories with recognizable or abstract sounds, interactive sonification, real-time data exploration through sonic feedback. For this project, we will mostly be focusing on parameter mapping and some interactive sonification. I wanted to mention the Sonification Handbook. It's a really interesting and amazing resource. You can access the PDF with a link that will be provided. I also encourage anyone who is interested in these subjects to attend or reference the resources provided by ICAD, the International Community for Auditory Display. ICAD is a forum for presenting research on the use of sound to display data, monitor systems, and provide enhanced user interfaces for computers and virtual reality systems. So I already talked about some of my work, but I wanted to dive a bit deeper into the methodology behind this particular work, Orbitz. Orbitz is a data-driven generative instrument that I built in Max MSP to transform the rotational patterns of Venus and Earth as they orbit around the sun into immersive visuals and soundscapes. It is designed to explore the natural patterns inherent in the cosmos, and I have performed it in spatial audio arrays ranging from 8 to 140 channels, and also within full dome environments. The instrument uses a dataset developed by Hartmut Worm, first published in his book Signature of the Celestial Spheres, along with data from the HYTRAN dataset, which simulates the transmission of light in the atmosphere and is calculated for different molecules. The performance utilizes an iPad and Menu gloves, enabling real-time interaction and expression. So you can see the datasets here. On the left is the dataset from the Signature of the Celestial Spheres, and on the right are graphed images of oxygen from the HYTRAN dataset. This image is created by drawing a line between Venus and Earth as they circle the sun for each day marked in Hartmut Worm's dataset. As you can see, they create a really beautiful pattern. And so I thought it would be interesting to see how that could be translated into sound. I processed the two datasets using a few different methods and generated 10 different tones that I can alter in a variety of ways in real time. One example of a tone I created is something I call Triangles Yay. It's a playful exploration using a simple triangle wave oscillator. For this sound, the frequency or pitch of the oscillator is controlled by the distance between Venus and Earth. As we move through the dataset, each consecutive data point is played through a different speaker in the array. The larger the speaker array, the more data points are played simultaneously, creating rich phasing and beating effects that can be experienced differently depending on where the listener is and how they are moving within the space. This is an example of using a direct-to-speaker approach of audio spatialization over using 3D audio algorithms. I also like to develop tone clusters that can be spatialized and animated within an ambisonics field. For this instrument, I created two tone clusters, one for Venus and one for Earth, and used the relative positions as they orbit the sun to spatially decode sound across variable speaker arrays using ambisonics techniques. To support flexibility and scalability across multi-channel configurations, I relied heavily on Max MSP's MC objects, which allow me to efficiently manage dynamic routing and to adapt to a range of speaker setups. I'll be diving deeper into some of these techniques in our session today. If you're curious to learn more, I wrote about this work in a paper published in the 26th ICAD conference in 2021. I will provide the link for that as well. NASA has been diving into sonification as a means of exploring their vast amount of universal data. Let's check out some of the data sets they have available on their website. So if you come to this link here, Sonifications, there are many different sonifications that NASA has created using a lot of different data sets. So we could just kind of choose one here, the sonification of ARP 140, and see how it sounds. You can see that in the description, it talks about how scientists sonified the data in this image, assigning pitch to color for the image as a whole. Blur light is higher, redder is lower. Pitch is mapped to brightness for the resolved stars and background galaxies based on their apparent size. Objects that appear bigger are lower and smaller are higher in pitch. Brighter light is louder throughout the image. Of course, they're mapping it a bit with different instruments and different tones and kind of scales. So there's definitely some really interesting ways you can look to explore sound. Let's listen to one more, this RS Puppies. Again, you can read the description on how they did this sonification. But it's a fun place to explore how NASA is using sonification to explore some of their data. They also have this app, Hearing Hubble, which allows you to be able to create your own sonifications. So we can say, we can kind of choose which direction. I like clockwise. If you want to do brightness or color, we can stay on brightness. What sort of harmony you're in the mood for. Let's say majestic. Sound wave, it's gentle. And let's do a piano. Maybe let's do a little bit on the slower side, and we can play it back and see how that sounds. I encourage you to come and play with making your own sonifications now. This wraps up our segment on sonification. If you would like to engage further with this topic, you can read the Sonification Handbook, and you can also play with NASA's Hearing Hubble Sonification web app. This next module is about datasets. We're going to talk about how to source data, where to find data, and how to then to be able to use that data to create interesting sonifications within Max MSP. So let's get going. So where do we find data? How do we source it? How do we use it and create anything useful out of that data? So for the purposes of this workshop, we're going to go to NASA's website and use some of the data and explore some of the data that's available there. So NASA has an amazing wealth of data. This is the NASA Open Data Portal that you can get to by going to data.nasa.gov. And here they have a giant data catalog. When you click on that, you see that there's 26,273 data sets found. That's insane. You can, be able to go through this, try to sift, around and see if there's something that's interesting to you, something that sticks out. You can search if you'd like to. You can also access some of the tags. Now, if you don't really have an idea or you're not quite sure what you're wanting to do, this could be a little bit overwhelming, searching through all of these data sets. One of the other places I like to go is just to the NASA website itself. Here you can go to news and events and the news releases. In the news releases, there are tons of articles that are talking about different things that are going on within contemporary NASA research and things that are happening there. And maybe there's something there that speaks to you. So I picked out for this particular workshop an article about NASA's mission to help predict the severity of solar storms. If you remembered back in April 23rd, 2023, there was a very strong solar storm that created aurora borealis all the way down into New Mexico. And if you live in New Mexico, you know that is not a common occurrence. So I was interested to kind of explore more about solar storms and how, and what they can kind of do and be able to work with some of this data. So this is a really interesting article. If you would like to read through it, you can. And when you are going through these articles, you can also look for papers that are published. And these are actually a great resource for finding data. So I'm going to access this paper here. The Gold and Sabre Observations of Thermosphere Composition and Temperature Responses to the April 23rd, 24th Geomagnetic Storm. And you can also download this paper, read through it, try to understand it. But one of the interesting things to look at is this Open Research tab. If you come down here, there's data availability, and you have this IMF data from this website here. So I clicked on this link. It brought me to the Goddard Space Flight Center with different data sets available, but I went to this heliophysics data portal. when I got here, I went to this website here. And now we found a software package for computer-aided CME tracking. So Cactus is autonomously detecting coronal mass ejections in image sequences from LASCO. If you click on some of these links, you can see, oh, here, this is a nice data set. This might be something that we could use to sonify. Now, there's not a lot of data kind of available here. So we're going to go back and maybe look here. So yes, this is a much larger data set, and I think we can kind of sift through it and do some really interesting things. So to be able to get the data set and onto your computer, you can do a very simple select all, copy, and then you can open a text editor or something like that and create a new document, and then save that document on your computer, and you can paste the data set in there, and then yes, you can save it. So let's save this data set. So this one is from August 10th, 2025. So I'm just going to type in 2025, August 10th. And then label it CME LASCO. I'm just going to save this to my desktop now, and we're going to come back to it later when we dive into Max MSP. Once you have selected a data set to work with, the first step is to try and understand the data. What does the data represent? What story is the data telling? What are the different variables in the data set, and what do they mean? What is the unit and scale of measurement? What is the time component? How is the data being measured over time? Once you feel like you have an understanding of the data, you can start to think more about the data structures. What is the dimensionality? How many variables are there? How do they relate or not relate to each other? What is the range and distribution? What are the minimum and maximum values? Is the data clustered, flat, skewed? Do certain variables move together? Are they correlated? At this point, we are ready to begin thinking about mapping considerations. How do we take these data points and map them to sonic variables? The data might need to be processed before we can begin mapping. Sometimes we will need to scale the data or normalize the data to map appropriately to the value we need to control. If we are trying to map to pitch, we may want to scale the data to fit within the perceptible auditory range. If we are trying to control loudness, we may normalize the value to a logarithmic dB range. Are there certain data points that might more naturally fit without having to be scaled or normalized? That might help determine some of our mappings as well. Temporal resolution can be something that you can control dynamically, or maybe it is static. How quickly do we want to move through the data, or should this be dynamic? Also, relevance. Do we need to use all the data points, or are there some we won't use? So what are some sonic variables that we can map data to? There is pitch and frequency, which are higher or lower notes, amplitude and volume, timbre, duration, panning, spatialization. So let's start to put some of this information to use. We're going to move to Max MSP, and we're going to start working on importing and parsing data, as well as beginning to explore some basic sonification. All right, we're going to start with our first coding break where we're going to import and parse our data. So first thing that we're going to do is come over to Max MSP, and we have our blank canvas. To be able to read our data, we're going to create a text box. And then we're going to need to create a message, read, that will allow us to open our data set. So that will give us a box to be able to explore the data, so navigate to wherever it is on your computer. And then we are going to open that file, and voila, we now have our data imported into our text box. So the next thing we're going to want to do is to start to be able to move through this data set. So I'm going to connect a print to the text, and then we're going to create a message line with a variable value, and a integer box. So let's connect all of this. So now if we open up our console and we type 1, we are able to read the first line of our text value, and we have it being printed over in our console. So if you look at that, that doesn't make a lot of sense. But if you go up here, you can see in our data set that our data actually doesn't start until line 34. So let's move down to line 34 and see what we get. All right, that's starting to look like some data. So the first thing we need to do is start to actually parse some of this data out and be able to clean it up a little bit. So it's not going to be super easy to work with. The first thing we're going to want to do is to get rid of this value set. So let's create a route set, and that will route set out of it, out of that line of data. So let's connect these now. Okay, now if we do 34, we no longer have set in this value. The next thing we need to address are these vertical bar lines. That's also not something that we need, so let's try to get rid of it. So to do that, we're going to use this regexp box. And this box kind of allows you to process different inputs using different rules for being able to move through kind of matching and substituting out different inputs for different outputs. And so if we come into the meta character part of our help box here, you can see that this vertical bar line is actually a special character. So to be able to substitute this special character, what we're going to need to do is use these double backslashes. So all we have to do is come over here and we're going to do double backslash and our vertical bar and do at substitute. And I probably spelled that wrong. I feel like I've done that. All right. So now let's see what happens if we connect that to our print. All right. Now it has just removed all of the vertical bar lines. You notice we didn't have to necessarily put anything after substitute because all we're trying to do is substitute the vertical bar line for nothing, really. We don't want it to exist. So now that we've got our data kind of coming out in this different, or we've removed all of the different elements of the data set that we don't need or want, we can actually unpack it. So let's unpack this data set. And we need to start thinking through what we need to unpack. So the first value, I think this kind of looks like it's coming in more as a symbol. So let's try symbol, symbol. And then we have 1, 2, 3, 4, 5, 6, 7 floats. So 1, 2, 3, 4, 5, 6, 7 floats. And then the other thing we want to notice with our data set here is we have this halo value that sometimes occurs. So if we want to capture that, let's add another symbol at the end. And let's see what kinds of values we are getting out. So we'll connect a bunch of message boxes to all of these outputs. All right, let's see what happens if we hit 34. Great, one more message box. All right, it looks like we're getting some data. And to test out if we're getting this halo line, let's go all the way down to, it looks like line 55 and see if we get something. And we're getting it. So now we have just taken our data set and we have been able to kind of process it. And now we can start to work with these values and assign them to different elements to Sonify. Okay, so the only other value that we might want to do something for is this value here. So when we removed the vertical bar line, it actually just created one kind of string of numbers. So one way, I think there might be a few different ways to approach this, but for this, I'm going to use a from symbol, and I'm going to do an at separator and vertical bar, and let's see what we get. Sorry, we need to connect this right out of route set. So let's try that again. All right, great. So now we have two different values coming out of this. So all we need to do now that we have kind of a list is use ZL slice to process our list at 1. And so this is going to divide our list into two lists. So for two values. So let's do that. And let's try that again. All right, now we're getting those values separated. So we can leave it like that. The next thing that we're going to do is we're just going to add sends to all of these different data points, so that instead of having to route them with patch cords around our patch, we can just use the receive values to be able to do that. So let's just take a little bit of time and attach sends to all of these values. And I'm just going to label them after their actual data values in the data set. All right, now that we've got our patch all set up with send values, the next thing we're going to want to do is to be able to move through this data set without with a counter or something like that. So we're going to add a counter. And again, remember that the data starts on line 34. So we're going to create a add 34. So now if we bang this counter, you can see we start at 34, 35, 36, 37, and we keep going up in our data set. So I'm going to add a metro to this, and with like a 4n value. So we're going to use this related to a global transport. So let's connect that, and we're going to create a toggle to turn this on. So now if I turn this on, you see it's not really doing anything. That's because we need to open up a global transport. So if you go into the help box here, I like to kind of just copy and paste this global transport into my patch, close that down. And you can see we have our global transport here, and now we can activate this. And once we activate it, now you can see that we're moving through the data set. One of the fun things that you can do with this is be able to use this to change the tempo, which means how quickly you're moving through the data set. You can also change kind of the rhythm, your time measurement. And you can kind of move through the data in a more, with maybe a little bit more swing or a little bit more kind of straightforward. It gives it a little bit of a rhythm. So this is how we're going to kind of start to be able to work with our data. So let's take a break, and we'll come back for learning a little bit about now how to take this data and do some stuff with it in working to sonify it. All right. So we're back with Coding Break Sonification Part 1. So let's come back to our Max patch. As you can see, I've cleaned this up just a little bit, and I've kind of created a little comment box over here that gives us kind of a little bit of a understanding of some of the different data sets that are the data values that we are working with. So if you come in here, you can see this is all of our what we just built, but we've kind of put it into a subpatcher so that we can start to focus on the sonification part. So the first thing that we're going to do is start to work with being able to sonify a synthesizer. So I really like to just work with, I think that's one of the more interesting approaches to sonification. I know that there's a lot of different ways that you can sonify sound, but for the purposes of this workshop, we're going to focus on working with oscillators and actually just controlling tones and tonalities and pitches with direct oscillators. So let's start with a cycle, one of the simplest oscillators, a cycle wave, which is a sinusoidal oscillator. Let's attach to that I like to use live.gain, and we will create a DAC and attach that. So to be able to control the cycle value, we will need to be able to use some sort of one of these data sets. We'll use that to control the pitch. So I think if we look at the velocity data point, this actually looks like it moves through the audible frequency spectrum. So we don't really need to do anything with that value. We can just use it as is. So why don't we just try connecting that value to this first part, which controls the frequency. So let's receive V. All right, and now we're going to turn this down before we turn our thing on, and we'll start playing our data set. If we want to get it out 2 years, we can just there. So you can hear very simply that our data is now controlling the pitch value of our oscillator. Now, that is somewhat interesting, but it can get a little bit boring after a while. But what if we try some other oscillators, like a triangle wave? How does that sound? I think a triangle wave has a little bit different character. We can also use a sawtooth wave. And, we could try out some of these different data values. So if we create receives for maybe the variation of velocity over the width of the CME, dV, you can attach that and see how that sounds. So you get the point. We can start to just sort of attach and play with different waves forms in this way. Again, for the purposes of this workshop, we're going to focus on the triangle wave because it's one of my favorites. And let's actually open up the help box for this triangle wave. So you can see that the inputs you can change are, you can set this frequency value. You can also set the duty cycle. So let's try doing, let's actually see what happens if we use two different values to control the frequency or the duty cycle. So the duty cycle, you can see that if we change it here, I'll turn the volume up a little. Here it changes, but it really creates the most change between 0 and 1. So let's see if any of these values are between 0 and 1. No, they're not. So we don't have any values that are kind of operating within that range. So one of the things we can do, let's go back into our data patcher. And we're going to use the trough and peak objects to be able to choose one of, to be able to find the min and the maximum values of one of our values so that we can then scale that value in between 0 and 1. So let's pick a value that we think might be interesting. We'll stop our data for the time being. Again, if you kind of look at your data set here, we have this, principal angle, angular width. I think that might be interesting to work with a little bit later on for some different spatialization elements. You also have duration, which is, just kind of a 0, 1, 2, 3, 4 value. Maybe there's something here we could work with. Or, we have some more we could use one of these other velocity numbers. And we could actually take the same velocity number. So actually, let's do that. We'll take V. And we're going to figure out what the trough and the peak are for V. So if we connect these. And now for trough, because it will output the lowest, let's just give it a starting value that we know is within this set so that we can make sure that it will output something below that. So let's start it at 345. And actually, we're gonna add an iter value before this because we're going to use a dump message to be able to dump all of the data from our text box out and through our messages or through our here. So let's create 2 float boxes actually, in case there are any floats. I don't think there are, but just in case. So this might take a little bit just because it's a large data set, but hold on with me. All right. So it has now kind of moved through that data set and it's created a value, given us a low value of 0 and a high value of 2027. So now we can use this to create a scale between 0 and 227, and we will output a number between 0 and 1. So now let's put this over here, and we could do a new S like scale B. So now if we come over here, let's try controlling the frequency with the normal V, and we'll try the scaling the duty cycle with the scale B and see what happens. So you can hear we're creating a little bit different tonalities as we're kind of moving through this. So that's maybe one interesting thing we could kind of play with, is being able to control this duty cycle with another value, or with one of the data points, so that can kind of create a little bit more texture with this triangle wave. So this is a way that we can create maybe a little bit more of an interesting tonality with this triangle wave. So I'm going to open up the help box again here, And let's go over to this sync. So here, let's listen to what this is sounding like and what's going on. So you can see that there's some cycle objects now that are kind of attached to this triangle wave. And then you have a phaser that's also controlling this kind of last box here. So let's see what happens when we change some of those numbers. So there's some kind of cool things happening there. Now, I wonder what happens if we start to attach some of our data values to these different objects. So we can try to find ones that are matching, or we can move to some different data values that we haven't used before. So feel free to kind of choose different data values that you'd like to play with, and I'll do the same. So you can see that you're starting to get some different tones. Of course, we're using some larger numbers. So then that's going, where I think if you use some of the lower values with the cycle, something in between, the 0 to 1 range, you'll get, a different kind of tone. So play around with trying to take, trying to scale different values and sending those to the different, kind of as different data points to some of these different sounds. And so this is, I think, kind of where we're going to start with our first lesson on sonification. So now it's time for you to go and play. This wraps up our module on datasets. For further engagement, you can explore the data resources on NASA and any other data resources that you are aware of, and choose a dataset that sparks your interest. You can then parse and prepare the dataset for use in Max MSP and begin to play with mapping data values to sound parameters. All right, now that we have gotten some data into Max MSP and started to play with mapping some of that data to different sound parameters, we're going to explore how we could incorporate immersive audio. To begin, we're going to start with exploring psychoacoustics and binaural audio. So what are psychoacoustics? They speak to how we perceive audio and specifically how we perceive and localize sound sources in our environment. Interaural time differences measure the difference in arrival time of a sound to each of our ears. This specifically helps us locate higher pitched sounds in a horizontal plane. Interaural intensity or level differences measure the difference in volume between each of our ears. This helps us to locate lower frequencies on the horizontal plane. On the vertical plane, the shape of our ears and also the reflection of the sound off our shoulders, our head, help us to locate sounds on the vertical plane. So if we're trying to figure out if something is above us or below us, if something is in front of us or behind us, our pinna in our ears, or the shape of our head and the shape of our ears kind of help us to be able to do that. So now we're going to talk about binaural audio. Binaural audio recreates a three-dimensional sound field based on the psychoacoustics of how we perceive sound. Recordings are typically made using in-ear microphones placed on a dummy head or even on your own head to capture spatial cues. Visualization of 3D audio are created using HRTFs, head-related transfer functions, which model how sound is filtered by the shape of our head, ears, and torso before reaching the eardrum. HRTFs use impulse responses recorded of sound recordings in the ear to virtualize the effects of the head-shoulder pinna on sound sources in a headphone experience, thus creating a more three-dimensional version of the sound source. Everybody's heads and pinnas are different, so not all HRTFs are going to work for everyone. There's a lot of research happening around creating personalized HRTFs so everyone can have an HRTF that is unique to their head and pinna shape. SOFA is a file format for storing spatially oriented acoustic data like head-related transfer functions and binaural or spatial room impulse responses. SOFA has been standardized by the Audio Engineering Society. It can also store more complex data like directional room impulse responses. There are large datasets of SOFA files that are accessible online. We will now explore how to use SPAT to create a binaural output and how to download and experiment with different HRTFs.
All right. Now we're going to move into our coding break, getting started with SPAT and binaural. So let's head on over to Max MSP. All right. So once we're in Max MSP, we're going to create a new spat5.binaural panning object. So, one of the best ways to learn more about these objects is to just click on the help file and open it up. So voila, here we go. Now, if we turn our audio on, we can kind of turn this up a bit, and let's play some pink noise. So we can hear some pink noise in here, and we can look at some of the different things that are connected to our binaural object. So we've got the SOFA loader. Remember, we were talking about SOFA files. So let's see what happens if we bang one of these. So we have some different built data HRTFs that are playing, and it changes the sound quite significantly. If we double click on the SOFA loader, we can go here and we can look at all of these different SOFA files that are available to be used. Now, to be able to use them, I'll turn this pink noise off. To be able to use them, we're going to need to download them. So if you haven't downloaded them already, you can just click on one and download it and, you have IRCAM SOFA catalog. So we can just put it right in there. And it'll take a minute to download, but you can get that going. The other thing we can do as well is if you come over to this here, you can go to sofaconventions.org and this here open, which this kind of talks about SOFA and some of the basic elements of that. You can also click on this one, and this is where you're actually going to find the contents of the archives. So if we go in here and go in here, you can see we have the 192, K, 32K, 44.1, 48, 88, 96. I like the 96 realm. Again, you don't need to download everything. So maybe you just download some. So we can download this archive.zip. It will take a minute. But while that's downloading, we can talk a little bit more about how to actually control this. So the spat5.binaural is really just going to be allowing us to create a binaural panning environment. And again, we can then load in a SOFA file, or these are some of the built-in HRTFs that we can use with this binaural panner. One thing I really like about SPAT and about this panner is the fact that you can load in different SOFA files and HRTFs, and it's not just one proprietary format that you're working with. The other thing we're going to talk about is this viewer over here, the SPAT5 viewer. So let's double click on it. When that opens, you see we have this viewer box, and this is actually where you can see either your sources or your speakers. Right now, we're just seeing two sources. You can kind of look at this here. So it says init with, and then you have in quotes source /2. And then you also have /source /1 /AZ -30. The reason that this is kind of formatted in this way has to do with the fact that all of the SPAT objects are OSC controllable. We're going to talk a little bit about OSC at the end of this workshop, but I just want you to kind of understand that that's one of the reasons why it's formatted that way. So let's come back into here and we can create our own Spat 5 viewer. So if we double click on this, it just kind of creates these two windows. Again, we can also look at the help file for this. And there's a lot of stuff you can kind of dig into. We're not going to dig too deeply into all of this right now, but to start out, we'll dive into this source one here. So you can see it says spat5.viewer at init with source number 8. So this actually has 8 sources so that are immediately kind of defined in our plane. And so each source you can assign a different audio value to, and that will allow us to be able to create, be able to pan them around in this virtual environment. Also, you'll see here's a nice little kind of little UI for being able to control the viewer. So you go to open, status. This shows you all of kind of the status values. You also have floating, which means this can either stay in front of all of your screens or it gets kind of put behind. And then you also have kind of your help, snapshot, shortcuts. I encourage you to kind of dig into some of this more deeply. We won't be doing too much of that today. I just want to mostly get you kind of going with some of these objects. So let's do, we can actually copy paste because sometimes I'm lazy and I don't like to write in everything. So we'll copy and paste this here. So you have, again, at init spat5.viewer at init with, and then source number 8. So we can change this. I think right now, let's just start with 2 because we have this cycle object and this triangle object that we created, and each of them are just outputting one individual signal. So we'll put those 2 together and we can kind of connect this. Actually, you'll notice here that there's these through inputs that Spat uses all the time. And again, it just allows for a little bit simplified wiring of multiple wires to, kind of for the subsystems. So if you have like a bunch of different stuff that's kind of coming into one thing, it just kind of allows like an easier kind of routing for that. So you can use them to help with your patching. So let's go back here. So we might as well create a through, and we can connect this here to begin with, and here as well. And then also I'm going to copy and paste this little UI because it's a lot to make it otherwise, and we can connect that as well to our viewer. Again, let's create a through and connect that. So now let's see what we have. So if we open this, we have 2 sources. They're kind of placed in these different locations, and we can see that. And so we can close that if we want to open it, and we can create it floating. So then it's just going to stay in front of us no matter kind of where the patch is moved to. So the next thing that we will want to do is we actually want to attach a sound source to each of these objects. So to do that, we're going to need to define, let's go back to the Spat binaural. So we need to actually define how many sources there are. So let's do at sources 2. And we have that matched. And now the next thing is we want to be able to control the position of these sounds. So now before we go there, we're going to just connect our sources so that we can connect just directly. Here's our input 1, and then here's our input 2. So let's actually, instead of having this going out the DAC, here, we'll move this over here. And if you hold over left, and this is right. And so binaural works best when you have headphones. So make sure you're wearing headphones for this to be able to kind of get a feel of it. And now let's pull up the sound and see if we hear anything. You can kind of move it around and see what happens. We can pull that down. We can also move this up. And you can kind of hear that moving around as well. We can play through our data, and so you can kind of hear this changing a bit. You can kind of decipher how good or how not good the decoding is working. Again, I think the next thing would be to connect our different HRTFs. So we're going to build that out here. Okay, so let's turn the volume up again. Let's see if we get any kind of different. So different sounds are going to have a different feeling, or like different way that they're decoding. So let's see if our files have downloaded yet. Usually the ones that have downloaded are at the top. I'm working off a computer that I don't have them downloaded on yet. So let's see if we have our zip file. Okay, it's still going to take some time, but for now, if you want to play with just your own kind of downloading your own SOFA files and then playing around with the way that that sounds and moving it around, feel free to do so. The last thing we're going to do for this section is we're going to attach a data point to being able to control the position of these objects in the spatial environment. Okay, so let's come back again to the viewer and open up the help file. Okay, let's go back to source, and we can kind of see, we'll actually turn floating off here so that we can bring this in front. So let's open up this viewer. Now, if you see these buttons over here, and start playing with them, this is what's actually going to move the sound around. And so you can see in a circle. And then you can kind of see, it can also move out and down. So you have here, this is, again, \azimuth. So this means that you are controlling the azimuth of this space. So the spat objects, and traditionally, most three-dimensional kinds of spatial algorithms operate on either using a Cartesian coordinate system or a spherical coordinate system. Personally, I like using the spherical coordinate system, but you can also use a Cartesian coordinate system. The difference being that one is operating on the azimuth elevation distance plane, and the Cartesian is going to be operating on the XYZ plane. So it'll be a little bit different how you're kind of controlling things and how things move around. The spherical, of course, is definitely a little bit more, I think, useful kind of. It's what we're more used to working with in our brains as far as for kind of a spherical environment. So we're going to stick with that for right now, but feel free to explore using the Cartesian coordinate system. The difference is that you're going to be using AED versus XY or XYZ for controlling the kind of positional sources. So you can see here that this is just doing azimuth $1. So this is just directly controlling the azimuth. You also have this message box here where you are controlling, it's just doing the AED position, but you could control the distance and have that change. You could have a set elevation and then just move stuff around the azimuth plane there. So you can kind of play with what makes sense. I think for the purposes of this, we're just going to use the azimuth object. So let's do that. So let's connect a message \azimuth and a $1 value. And we'll create a integer. So now, let's open up ours and let's see what happens. And sorry, we got to prepend this with source 1. So now let's see. All right. So now we are controlling the position of our azimuth. So now we can also do this for source 2. So let's just copy this over and we'll just change this out to 2. And again, we can use our handy through to just make the patching a little bit cleaner. And now let's see. All right, so that's now being controlled too. So if you remember, 2 of our data points are actually measured in angles. So angles are actually a perfect representation of a Cartesian coordinate system. So let's actually connect those to these sources and see what happens. All right, so now they're moving around in space. So let's try and okay, so now we have 2 different sources being controlled by different data sets for being moved around space. So we're going to leave that here, and then we're going to move on to the next part of our workshop.
This wraps up our module on immersive audio, psychoacoustics, and binaural applications. For further engagement, we can download and try out different HRTFs. Which are your favorite? Which seem to work best for you? Make a note of them. Experiment with mapping data values to spatial sound parameters.